Welcome back to the track. In our last unit, we were like security guards at a VIP gate, the quadrupole, picking one person at a time and telling everyone else to wait. It was precise, but slow. But what if the stadium is on fire? What if you need to identify everyone instantly? You don't filter them one by one, you make them all race. Welcome to the world of time of flight, or TOF. This is the speed demon of mass spectrometry. TOF is the only analyzer that sees every ion from every pulse, turning time into the ultimate ruler for absolute mass accuracy. While the quadrupole is a sniper, the TOF is a wide-angle lens. It gives you the whole story in a heartbeat. Today, we are going to master the Formula 1 of analyzers, where speed isn't just a shortcut, it's the foundation of high-resolution science. To master the logic of speed, we navigate 4 strategic sectors. Chapter A, the equal kick, the physics of kinetic energy. Chapter B, the long runway, navigating the flight tube. Chapter C, the ion mirror, why the reflectron is the fairness committee of the race. And Chapter D, the nanosecond finish line, how HRAM provides your ROI in untargeted discovery. The race begins with a pulse. In the ion source, we apply an accelerating voltage, V specialist's insight. The physics is simple but profound. Potential energy ZV is converted into kinetic energy 1/2 mv squared. Because the energy is constant, velocity becomes a function of mass. We've turned the who are you question into a how fast can you run competition. Look at the math. Velocity is inversely proportional to the square root of mass. This means if you can measure the time it takes to cross a fixed distance, you can calculate the mass with surgical precision. Mentor's tip: in a TOF, time is money, specifically nanoseconds. We aren't measuring weight on a scale. We are timing a journey. You don't need a balance. You need a world-class stopwatch. Once kicked, the ions enter the flight tube. No more electricity. No more pushing. Just pure momentum. Imagine a marathon, where the light sprinters pull ahead of the heavy powerlifters. The longer the track, the more the distance between them grows. In a high-end lab, we use tubes up to 2 meters long. Why? Because distance is the amplifier of truth. The more time we give them to race, the better we see the difference. Here is where the pro leaves the amateur behind. Identical ions might start at slightly different speeds. Without help, they hit the detector at different times, creating a blurry peak. Enter the reflectron. Mentor's tip: it's the fairness committee. Fast ions penetrate deeper into the mirror and take a longer path. Slower ones bounce back sooner. They all arrive at the detector at the exact same nanosecond. Why care about nanoseconds? It gives us high-resolution, accurate mass. In a modern TOF, we measure mass to within 5 parts per million, ppm. This is your chemical GPS. At 5 ppm, you can distinguish CO from N2. This allows for untargeted discovery, identifying new drugs or biomarkers without needing a reference standard. You are reading the history of the sample directly from the clock. How we record the finish matters. Older systems use TDC, which are like simple counters. They get blinded by high signals. Modern systems use ADC. These sample the signal 4 billion times a second, capturing the full pulse shape. If you are doing high-concentration quantitation, you want an ADC system for the dynamic range. The method of timing determines the limit of your truth. Have you ever felt like you were missing the big picture? That is the frustration of a selective filter. But the TOF gives you the whole story in a heartbeat. It sees fragments, isotopes, and background all at once. By mastering the speed demon, you move from being a target hunter to a discovery architect. You aren't just following a map, you are drawing it for the scientific world. Summary: the power of the pulse. We've mastered the equal kick, the physics of the runway, and the focusing power of the reflectron. Remember, don't blink. In the TOF world, speed is accuracy. You are now equipped to navigate high-speed discovery with absolute structural certainty. Carry this racing logic back to your bench and see what others are missing. We've mastered the race. We know how to time molecules at the speed of light. But what if speed isn't enough? What if you need to measure the weight of an atom so precisely you can trace its origin to a specific mine? Join me in Module 7-3, the atomic scale, where we master magnetic sectors. Sometimes, the biggest magnets tell the smallest truths. Any final questions on the racetrack?